spring are made from real material. If you increase the x too much, then the spring breaks, and this is because of physics, right? There are more detailed model that's like model by like every atoms of the spring, but here we just have a simplified model for the spring, right? And well, I guess the reason that I made a perhaps provocative statement that physics theory is just a model, because I think it's I think for people who study physics, they have a tendency to think of the rule of physics as God-given and like immutable. But really, what we're doing here is that we use mathematics to guess models, and preferably simple models, to explain natural phenomena, right? So both like classical mechanics, quantum mechanics, these are our models. And I guess if you are not an experimentalist, you don't really update your model systematically. Maybe you just have some kind of thought in your head that, oh, maybe this is wrong, this is right. But maybe you, not maybe, I mean, I guess nobody actually like write down your probability of, I think this model is right with classical mechanics is right with this probability and something like that. Yeah, but we just have it in the back of our mind, right? But in actuality, yeah, you would, if you like a learning robot, you should have some algorithm to update your model too, right? Because we say that when we get in more information, we learn, but whether the lesson we learn from the information match the reality or not is also up to the class of the model that we consider. For example, I can people like toss a coin, right? And then say if the coin is fair, if I, somehow I'm not cheating, then the probability that the coins will land head or tail should be like 50-50. Even though everything can be, you can write down Newton's equation of, the trajectory of the coins and actually calculate whether it will land head or tail if you know every information about the toss. But say if you study a coin toss, and then your model is that there's only two events that can happen in the sample space, which is, the coin come up tails or head, then no matter how you toss, like no matter how many times you toss a coin, you're not going to learn about Newtonian dynamics. Yeah. Because the coin may land on this edge and so on. Yeah. Right. So maybe to emphasize this difference, let me like see. Yeah, I never remember how to draw dice. So if I am a probabilist and I see a dice, or I go into a gamble something, then maybe I will say something like, oh, if the bias, if the dice is fair, for example, then I can calculate everything, like some kind of expectation value, the chance that I will be winning, the chance that I will go bankrupt. But if you're a statistician, you will go in the room and then try to try to roll dice and try to figure out whether the dice is biased or not. What is the word I use here? I need to roll the dice. To figure out P. And I would argue this is not so different from quantum mechanics. The way that we learn quantum 101, we are sort of acting like a probabilist, because we say, if I know that the quantum state is psi, then I can calculate everything. But usually we never ask, how do we know that the state is psi or something else? And well, unfortunately, in this course, we will not go into too much detail about this kind of inference. But I think it's something that's always, in the back of people's mind. They just want to bring this out explicitly, that these are like two kind of different tests. And when you're interacting with the real world, like doing research on quantum state verification and quantum tomography, then you need both of them, actually more of this. Yeah, which we never ever like teach. So, but I guess to take, maybe to go back and take the lesson that I said earlier, well, to learn more about like quantum inference. So suppose you want to learn about quantum inference or quantum statistics, it would be very helpful if you learn about classical inference and classical statistics as well. Okay. Any questions so far? All right. Yeah, so for all that we talk about, I sort of assume that you already know or have an idea of what probability is. Otherwise, we cannot talk about it. But what really is probability? Well, I guess to be I will not go into the math yet. Yeah, so I guess the intuitive sort of understanding or meaning that we assign to probability usually is about some kind of uncertainty, some kind of randomness. But in this sentence, this thing, so what is probability mathematically is what everyone agrees on. As you know, it's a positive number, the sum to 1. It's already been settled by Kolmogorov. Yeah, you know Kolmogorov? So he's a mathematician who gave a rigorous foundation to probability theory. So it's in particular, he realized that probability is already in mathematics is something called a measure. And this is the same as like integration measure. And so if you go into and read a book, a mathematical book on probability theory, or in Wikipedia, you will first see that what is, you have to define what is a sigma algebra first, and the properties of things. But usually those stuff, the rigor is really only need when your sample space is infinite. But in the case where, for example, we like toy at dice, then our sample space is just finite and we don't really need to care about continuity or something like that. But yeah, every sensible notion of probability, it turns out that in the end, it needs to satisfy the Kolmogorov axiom, which we'll talk about hopefully today. But this is, but not everyone agree on what this means. For example, the mathematical theory of Kolmogorov, you can already prove some kind of asymptotic statement or some kind of asymptotic correspondence between probability and frequency, right, of an event occurring. And this is somehow, I think, what most people that like scientists that take statistics usually think of probability in this way. Well, at least when you do like calculation or do experiments. Because a lot of experiment is like in a control experiment, you have some kind of consistency, right? That you can set some kind of condition and then you can repeat the random trial and then hope to see like consistent pattern out of it. But usually the application of probability, if you think of probability as just frequency, the application of probability is gonna be pretty limited. For example, before this semester, I never know Lapat before. And I sort of like maybe I talk to him, I interview him via Zoom, and so maybe I have some uncertainty about his maybe physical attribute, for example, height, for example. Yeah, but does that mean that okay, you understand the frequency here, right? That if I have a probability of like 70 in 100, then usually people will think that, oh, if I have 100 things, then the statement, the proposition attached to that probability would happen like 70 times. But obviously this does not apply to the situation that I described here, because I don't have like a number of like many Lapas and with like different physical characteristics, and then I just pull them up, and then like 70% have this height or have this. Yeah, and actually this is something that historically is like a big debate about probability, meaning of probability, like surrounding this concept of frequency as well. So if you go back to someone that sounds pretty similar to Laplace, which is Laplace. I think if I understand correctly, he was the first one so to really apply theorem in probability theory, like Bayes theorem, to actually do inference. And for example, he would calculate he would give mass of the Saturn, but with like a confidence interval, with like, okay, the Saturn should have a mass in this range with this probability and so on and so forth. And people in the past were really confused about his result, because, well, probability means frequency, so but we only have one Saturn. So what does it mean to have a distribution of a mass of a Saturn. Or he also calculated the probability that the sun will rise tomorrow. So in particular, the P sunrise is the number of times you have observed sunrise in the past plus 1, and then divide by this plus 2. We are not going to derive this, and we are not going to ever use this in the class. But if you want to know, you can read some book, and this can actually be derived from probability axioms. But this is from some like classical perspective, and I use classical here in the world like classical statistics, right? Not classical physics. From the classical statistic perspective, this is a really weird thing because this probability, they used to think of probability as objective, as sort of like a physical property of something that maybe when, maybe they say that, oh, the property of when they toss a coin and the result come up here is 50 is related to some physical property of the coin, about the bias, about the weight or something. But for this, the property of sunrise, you would get a different probability, depends on who you ask, right? Because different people see different number of sunrises. So this probability cannot be ascribed the meaning of frequency. And this is more akin to the way that we use probability, or the word like probable in English language, which just express our uncertainty, our lack of knowledge. Right? And this is why Laplace is well known for his Laplace demon, right? Because he said that, oh, if there's a demon that knows everything, like in physics, like every position and momentum of every particle, then they can predict anything with like 100% accuracy. There's no uncertainty or whatsoever. Yeah, and so there are a camp of people that believe more in this like meaning of uncertainty. That is something in your head, and then you can use probability to sort of describe the state of knowledge or state of uncertainty in your head, and when you make decisions, so on and so forth. And actually, this is how I think classically, you can, well, I don't know if you would believe me or not, but and you don't have to believe me, but I think that classically it's sort of clear that every probability is subjective, in the sense that even a coin toss depends on your trust on the people who toss the coin, right? Because I heard that there's some kind of magic trick that can toss a coin and always get the result that they want. Oh, right. What I was going to say is that actually the way that we assign probability to like ensemble in statistical physics, or at least classical statistical physics, I would say is always subjective probability. And then it's left as an exercise to think whether you can say this statement when you know quantum mechanics. Yeah, some people say that quantum mechanics means this is the way that we can argue that there is an objective probability. because the probability would just be whatever you calculate from the Born rule. But some people disagree because, well, if you think like this, then if you think of quantum state as an analog of probability distributions, then quantum state is in your head too. Yeah. Oh, maybe is more clear that so I use this against objective, right? Maybe คือถ้าเป็นภาษาไทยยิ่งไม่ได้เลยเพราะมันแบบเป็นอัตตวิสัยภาวะวิสัยอะไรสักอย่าง so something objective is I would say is something that depends on the like property that is out there in the world. So suppose I say that I don't know this water is sweet or sour or something like that. Yeah, I would say it's a subject. Well, I guess I'm not going to say that people have different tastes. But yeah, there's like maybe there are actual sugar in the water or so on and so forth. But something like the value of money is, I would say, in some sense, is objective, because the value of money it's not really the value of the physical material that make the money, but it's the value that people agree that okay, this is the value of this banknote, for example. It doesn't really depend on any physical property. Yeah, and so now is that clear? So now, do you think probability is subjective or objective? Why? Subjective? Okay. Yeah. It's a subjective thing that is based on like agreement of people or like your state of knowledge. Yeah. The objective would depends on like the physical, the things that are really out there in the world. Wait, so do you think probability is subjective or objective? Or maybe you can tell me later. กี่โมงแล้วเนี่ยเชื่อไม่เป็นเล็กอะไรเยอะ Okay, so a really mathy way to describe this in more detail would be if we go to look at the Bayes rule. Oh no, discover white chalk. So the major two camps in statistics who believe in subjective and objective probabilities are called Bayesian and frequentist, respectively. And frequentist because they believe in frequency, right? And by the way, this is just like a straw man, right? Because usually people would be somewhere in between like extreme Bayesian and extreme frequentist. Yeah, and usually, or maybe I should also say like really like practicing statistician also wouldn't normally they also wouldn't care about the about the interpretation of probability. They just use whatever that is they need to do. Right? It's kind of the same with interpretation of quantum mechanics. There are many interpretations. So famously on, well, when I say famously, it's usually some quote from, maybe we think of quote from some history or some books, right? But this is famously a quote of Peter Shor from Stack Exchange. He said that, on Monday he can believe in one interpretation of quantum mechanics. On Tuesday he can believe in another interpretation, if that what inspire him to do the work in quantum mechanics. But okay, so this is more like I will try to give a more quantitative view of the difference between like the subjective and the frequentist view, which is, we start with Bayes' theorem. And this is something that we will talk about later, maybe today in like 30 minutes. And Bayes' theorem is really doesn't by itself doesn't have anything to do with Bayesian, because it's just a mathematical true fact. Right? And this is the way that you write conditional probability in terms of another conditional probability, so in the opposite direction. So now, but how do statisticians use this? So before this, so X would be like a random variable that describes data, and maybe data will describe the model, or sometimes they call parameter. And I will give an example soon. So suppose, let's say that I do this. So by this like property of X here, I just mean the property that the data will occur, right, irrespective of the model. And this is also this property of the model. This is really the subjective probability, the uncertainty of the model that you consider, whether if I should use this model or not, if like how much I believe that this model is true. And this quantity is what statistician, like classical statistician, would focus most about, and they call this the likelihood function. And they care about this precisely because this is really the only conditional probability that they can talk about in frequentist term. So in more detail, so when I say that theta is model or parameter, so usually when statisticians gather data, and they will try to fit some model, some curve to the data, right? And so they would already have some model, some popular model in mind. For example, like maybe the data is Gaussian or normal distribution, and that would be described by two parameters, right? The mean and the variance. And so the parameter here would be the set of parameters that define the distributions, something like this. And in the frequentist thinking, so in the class, like if you associate probability with frequency, it doesn't make sense to talk about probability of the parameter because it is what it is, right? If I have a spring constant, then it's whatever is in the physics of that spring. And so it only makes sense to talk about this conditional probability and not that one, because this one is, okay, assume that the world is according to this model, then this is the probability that I'm gonna get this data. And there we, like classical statistician will use the likelihood function to determine what is the most likely value of the parameters. That's why the name likelihood. So something like, okay, if it's like if you have seen like hypothesis testing, like and p-value and stuff. So it's like, oh, if we observe X, but our model, if I assume our model, then the probability of X is really low, then our model is probably not true because we maybe observe X a lot. But actually, that's not the question that we want to answer. We look at the real world and if we gather data, right? So we have X, and then we want to know how confident I am in this model or this parameter. So to get that probability, you actually have to use the Bayes rules. But by using the Bayes rule in this way, you get this thing that the classical statistician hate. It's called the prior, because to get your belief here, you already have to have a belief about how likely is this model. And so they will say, oh, this is exactly like the sunrise case. The probability of some model or like some theory of the world being true will depend on how much you already believe the theory. And so the classical statistics trying to get rid of this. But usually I guess I would say in my opinion, every decision, everything that we made, every prediction, based on some assumption. And it's better to be clear that we have an assumption, or like what assumption we have, instead of trying to hide it and then say that we are not biased. By the way, this is called posterior. Any question? Anything that you want to say? By the way, like this debate will not appear again. I just want to say it up front in the first class. Yes. This probability, yeah. I mean, this would maybe you can think of this as like a dynamical law. It's kind of like equation of motion of your belief. That if you already have initial belief, then upon observing data X, this is your new belief. Function is the same conditional probability. It is the same as the conditional probability here. Oh, yeah, this is just jargon. So this is just what statisticians say, and you don't really have to care about it. But especially they would make a distinction between, so they would write this as a function, but they would make a distinction between writing this as a function of theta or a function of x. And I think for likelihood it would be depend on x, I think. Yeah. But yeah, better consult a statistic book. All right. Well, I'm not sure we can get to probability today. Yeah. Well, you may ask like, well, if you want to relate it to the course, you can ask like, oh, is there a quantum-based rule? And I'll let you Google that. Okay, so that was the fun stuff. That was the prelude. Yeah, so now I want to talk, so maybe for the rest of this lecture is like, is it 30 minutes? It's 25 minutes. Yeah, maybe we can start to talk about probability. But before that, so probabilities are, okay, so probability are assigned to events, right? So we should talk about events first. This is really the same as a summer school, more detail. So you would have the set of all events, right? Sometimes called the sample space or the universe. So that when the set is finite, we can always break up this sample space into elementary or atomic events. And these are disjoint sets. So we partition them into disjoint set, right? So for example, if yeah, usually you just think of sample space as some area, like, and then you partition things in terms that, you know, each subset don't overlap with the other, then we can call it elementary set. But usually in the finite case, it's clear what are the elementary set. Like if I toss a coin, then it's head and tail. If I roll a dice, then it's 1 to 6, something like that. Right? And then before we can go on and like assign probability to set, sort of this underlying structure is the Boolean algebra of sets, right? Because you can combine sets together with different operations like union or intersection. And that's also correspond to logical operation as well. And by that, I mean, if I associate a set to some logical proposition, right? So maybe like A is there will be rain today, and not A is there will be no rain, something like that. So the elementary operation would be and or not, and or. So if I have an n of two set or two set or well, if we are talking about logical operation, then these are the logical operation between proposition, right? And then this thing, which I never remember, is it this way or that way? Yeah, that's right. And then in the language of set, we have this kind of symbol which is probably more familiar to us. And I don't know if you have trouble remembering this, but for me, I remember that this is like an A, there's an N. Actually, sometimes the set version, sometimes people would also prefer, sometimes they want to write it in terms of like something that looks like arithmetic. Like N would be A times B, and or A plus B. And yeah, I guess this is so basic that I don't really have to explain how this works, right? That, for example, if A and not A cannot be true at the same time, so it's an empty set. If it's A or completer of A, then this is the whole thing. Right? But before we move on to probability, I want to list some like the arithmetic properties of Boolean algebra first. And you can see if it makes sense to you or not. Idempotence, if it's a noun, then is it like this? It's already look weird. And then or is also commutative. Multiply first. Is also associative. Which means that I have 3 events, right? And then it doesn't matter where I put the bracket. So I can just say that, oh, it's just this. And the same for or. And then the other thing is called distributivity. So this still looks okay. It's like normal multiplication. But this I will come back to this. You can say. จะทำไหมนะไม่ทำเลยทำ and I will come back to this. Then I will note another thing. It's called duality, which I mean, so if I take so duality is about when I take the not or the complement, that if an event is a product or like and like this, when I take not, then it's turned into or. And conversely as well. So if D is A plus B, then not D. Yeah, and for this kind of things, so obviously you can make sense of it by like drawing Venn diagram, like right always. But I think this way of writing it also make a nice connection with quantum mechanics as well. So quantum mechanics, you cannot put it on a Boolean algebra Otherwise, it would just be just classical probability theory. But if you only consider, well, you cannot put it why, because there are incompatible measurements, right? So there are measurements that you cannot make simultaneously, change the states and so on and so forth. But if you restrict yourself to just commuting measurement, and by here I would mean a set of commuting projection operators, then the algebra of operators actually obey this, right? Does that ring a bell if you have seen this property in quantum mechanics before? Right, because if you have a projection operator which I will denote by P, then the property is P squared is P. Well, what about the second one? Well, it's a bit cheating because I would say P plus P is 2P, but because if you normalize it again to be a projector, yeah, it's just P, right? And so, for example, you can, I guess before I go to quantum mechanics, so how can you remember this, for example? So maybe one way is to say that, for the first line, it just look like normal like distributive product. But in Boolean algebra, there's a property, some kind of order duality that says that you can switch the operation between and or, and you will also have the identity. And in this case, so the second identity is precisely the first identity, but then you flip the multiplication and addition. Okay, now then go back to quantum mechanics a little bit. Well, how does this work in quantum mechanics? Do you see it from the algebra of projection operators? So maybe I want to do it from the other side. So let's say it's a projector onto subspace A. Let's go to that side of the board. Is it hard to see pink color? Okay, so how does this work, right? So you get all the product, and of course the product of the first one, it is just the same projector. Now you get this guy, PBPA, PAPC, PBPC. So then I'm doing this. So here I'm just using matrix operation. I'm not using like some weird rule. This is just matrix multiplication. And I can do this because this is commutative, right? So what is this guy? Yeah, right. And why is that? Because the identity already contains other projector. So it's just absorbed inside. So if I write in terms of matrix to illustrate, let's say there's only 3 events, A, B, C. Identity would be this, right? And then this guy, maybe this is the second event, and this is the third event. Then you sum, and then you get something like this. But then you have to normalize it to be a projector, and so it's just identity again. Yeah, and so when restrict to commuting projection operators, commuting measurement, we actually operator algebra are the Boolean algebra. Okay, can I erase this board? Right. Yeah, so I think that's enough for the set theory. Now we can start to put probability on sets. And how do we do this? So I will just start by the Kolmogorov axioms. But in like finite sample space, so you don't have to care about continuity and so on and so forth. It's just algebraic properties. But yeah, there are many ways, many axioms that you can put. So the point of the axiom is just have to have a small set of statements that you declare to be true, and then use that statement to prove everything else in the theory. Okay? So I would assign something called probability to a set, and the first axiom is that it has to be a positive number. The second one is if A is an event that is certain to happen, then the probability is 1. The third one, let me call it a sum rule. And this is to say that the probability of A plus B or A or B is simply the sum of the probability if A and B are disjoint, right? Right, because if it's not disjoint, then you have to care to subtract the overlap of these two too. And then the product rule, which is sort of the definition of conditional probability. So A and B is, well, if you remember how Bayes rule work, so this is you can write either way, I think. B okay. Which, as a note, in the usual way people write this would just be a property of A comma B, right? And this means both events happens at the same time, or happens simultaneously. And from this axiom, you can we can derive all other probabilities rules. From these axioms, which you will do in homework 1.1. But I'm just asking like two things, not like derive the whole probability theory. And by the way, do you ever wonder why the probability rules has to be like this? I mean, it could be, you could use other set of axioms, but why would it be reasonable? Would there be other probability theory that is also reasonable, that is not this one? อันนี้ถามถ่วงเวลา
condition of the event that we consider.
Which condition? Yeah, like for example, would someone be able to say that if I don't use probability, or if I use the notion of uncertainty that doesn't is not consistent with this theory, then I would make some stupid decision. Yeah, a stupid prediction. Yeah. Actually, that's something that we're gonna talk about tomorrow. แต่ตอนนี้มันเหลืออะไรที่พูดได้ใน3 นาทีหรือเปล่า
Case of the third axiom.
Yes, in the homework.
I just wonder why he
Well, usually for axioms, you would try to be minimal, right? That you would try to assume the least, and get the most out of it. Yeah. But yeah, the meaning that the meaning that is in the homework is because that statement can be derived from these 4. โอเคครับก็วันนี้ก็เท่านี้แล้วกันครับคนที่
from general case.
ใช่เพราะมันมี condition นี้อยู่
มี condition ถ้าเกิดจะมี case มันจะมีอยู่
ใช่
ที่ผมตั้งคำถามก่อนไอ้ที่ว่า subjective คือจริงๆคือผมไม่เก็ตคอนเซ็ปต์ว่า subjective เป็นยังไงด้วย
มันคือตอนผมพูดแล้วเปรียบเทียบกับ objective อะมันดีขึ้นแล้วมันงงกว่าเดิม มันเป็นมันจะมองว่าเป็นทางฟิโลโซฟีหน่อยก็ได้อะก็เหมือน objective มันคือสมบัติอะไรที่จะพูดว่าไงดีสมบัติที่มันขึ้นกับจะพูดภาษาไทยไงดีวะถ้าพูดง่ายๆก็คือมันเป็นสิ่งที่อยู่ในมันอยู่ในความเป็นจริงอะที่ว่าไม่มีใครไม่ว่าใครเห็นมันก็เหมือนกันอะหรือไม่ต้องมีคนเห็นก็ได้
เป็นcondition ที่แบบมันอยู่ในโลกจริงไป
มันขึ้นอยู่กับสมบัติอะไรสักอย่างที่อยู่ในโลกจริงอะแต่ว่า subjective มันคือ property ที่เรา subscribe ให้จากคือมันไม่ใช่สมบัติของเช่นสิ่งนั้นเช่นผมบอกว่าอะไรแต่ตัวอย่างมันโอเคแต่แบบไม่คิดมากแล้วกันบอกว่าหมาน่ารักอย่างเงี้ยคือความน่ารักมันไม่ได้เป็นสมบัติทางฟิสิกส์ของหมามันเป็นมุมมองของผมอะไรเงี้ยแต่จริงตัวอย่างนี้มันอาจจะ argue ได้ว่าพูดถึง block
มันก็หมายถึงว่า ไม่อยากมาพร้อมกับ distribution
ใช่
แต่ถ้าเป็นไอ้ subjective เราไม่รู้ distribution นั้นแต่เราต้องไป
ไม่มันคือไม่มี distribution เพราะว่า subjective มันคือมันขึ้นอยู่กับเรา
นั่นผมว่าเราไม่มันไม่ได้มาพร้อม distribution นั้นแต่เราต้องไปทำอะไรก็อย่างมันซึ่ง
งั้นถามผมคือถ้าเราได้ข้อมูลทุกอย่างเกี่ยวกับระบบนั้นแล้วสมมติว่า2 คนได้ข้อมูลทุกอย่างเกี่ยวกับระบบนั้นเขาจะ arrive ที่ distribution เดียวกันหรือเปล่า
ไม่ถึงเป็น
เพราะว่าถ้าคนมันก็จะมีแบบถ้าพวก objective Bayesian มันจะบอกว่าต้องตรงกันถ้า subjective Bayesian เขาก็บอกว่า probability คือเป็น personal ไม่ต้องตรงย่อย philosophy
เพราะจริงๆแล้วไอ้ตัว distribution ที่ฉันพูดมันก็ต้องหา
ผมเข้าใจว่า objective distribution นั้นมีอยู่ในธรรมชาติ
objective คืออย่างนั้นแหละมีใช่
แต่ไอ้ subjective ขึ้นอยู่กับไอ้คน
ก็ใช่ไม่แต่มันเป็นตัวอย่างที่ฉันบอกว่า subjective ก็คือเราต้องไปหา distribution นั้นถ้าเกิด distribution นั้นคือ100 คูณหารที่เราวัดก็ไปว่าเป็นแต่ถ้า100 คูณนั้นมันไม่เหมือนกันเลยก็แปลว่าขึ้นอยู่กับการวัดขึ้นอยู่กับความเชื่อม
ใช่อันนั้นมันคือ subjective ใช่ไหมพี่
อันนี้พูดถึงตัวอย่างที่ฉันรู้
คำถามทางปรัชญาก็อาจจะเป็นว่าถึงแม้ว่าคนมันจะไม่เห็นตรงกันแต่ว่าจริงๆแล้วมันมี objective distribution อยู่ในนั้นอย่างนี้เราไม่เกิด
ไปอธิบายว่าไม่ยกตัวอย่างพูดถึงตัวอย่างที่น่าสนใจเกี่ยวคือเรื่องแบบบอลลีกอะไรเนี่ย personal อันนี้ของ subjective ก็คือเหมือนว่าที่เป็นชอบแบบน่าจะมีโอกาสได้บ้างไม่อยู่กับ personal เลย
เดี๋ยวพรุ่งนี้ผมจะสอนเรื่องแทงบอลอ๋อไม่หรอกเพราะว่าเราก็ไม่รู้ว่า probability ไม่รู้ objective probability ที่ทีมบอลชนะอยู่ดีแต่คือว่ามันที่เกิดเมื่อกี้คือมันมีวิธีที่ derive กฎพวกเนี้ยจากการบอกว่าจากการไปเชื่อมโยงว่าไอความเชื่อของเราที่เป็น probability ที่เป็นเลขจาก0 ถึง 1มันไปเกี่ยวโยงกับความเชื่อที่เราจะแทงหวยว่าประมาณผมก็ไม่รู้ว่ามันมีเรื่องขนาดไหน
ของผมว่าเกมเนี่ยเทียบเท่ากับเลเตอร์แล้วก็จะสร้างกฎอยู่ได้จาก4 ตัวนี้
ก็ทางคอนเซปต์ก็แบบนั้นก็ได้
พอจะไม่ชวนก็ไม่ไป
ก็ไม่รู้ว่าคลาสแรกเป็นไงบ้างครับเพราะมันออกไปทางน้ำเยอะแต่ว่าหลังจากนี้มันจะไม่เป็นแบบนี้แล้ว
พรุ่งนี้มา
น่าจะมา
บ่ายครึ่งครับ ละพัดเดี๋ยวพวกแบบวิชา research methodology ที่แบบถ้าต้องให้ผมหาเปเปอร์อะไรก็เดี๋ยวมา แล้วก็ว่าใช้ Facebook ปกติหรือเปล่าไม่ใช่แต่ว่าดูเหมือนว่าดูใช่ไหมไม่ได้แบบมี account ไว้เฉยๆอะไรอย่างเงี้ยหรือเปล่า
ก็ดูบ้างไปถึงจะใช้ทำอะไร
อ๋อคือปกติกลุ่ม QIS อะเรามี Messenger อยู่
Messenger ดูเป็น
อ๋อได้
แค่ของคอนเนคชั่นอะไรครับใช่
เอาชื่อ Facebook ไป
อ๋อได้แต่ผมก็เจอแล้วแหละแต่ผมก็ แต่ผมยังไม่ได้แอดเฉยๆไม่รู้ว่าใช่หรือเปล่าครับเพราะว่าพวกแบบเวลา